Hi, welcome to my presentation at FLOPS 2022. I'm going to talk about improving type error reporting for type classes. So type inference is a useful mechanism in that it allows programmers to enjoy the benefits of static typing without having to write long and verbose type annotations. The downside is that if a program has type errors, then type error messages are usually very hard to understand and to use for fixing type errors. This paper tries to improve this situation with a focus on type classes and functional dependencies. I will first give a brief overview about what our approach can do, and then I will talk about how to find error fixes, and finally I will present evaluation results. So the research of type error debugging has a surprisingly long history, and we can see from this slide, just a few years after the algorithm W was developed, several researchers already started to work on this type error debugging problem. And up to today, in the past 4 decades, we can see that a lot of approaches from different perspectives have been developed. Interestingly, even with those approaches, the support for debugging type errors in type classes and functional dependencies is very preliminary. And I will use 2 examples to illustrate the current research status. The first example is this function called rank1, which has a parameter x, and in the body, it applies x to 2 values of different types. This expression has a type error, and if we load this expression into GC, we receive this error message. We can see that there are 3 issues with this error message. The first issue is that it contains inconsistent explanations. It reads like that the literal 1 gives rise to the type bool, but in fact it doesn't. And the second issue is that this error message misses useful information or concrete information for fixing the type error. For example, if 1 is indeed the cause of the type error, then how should the programmer change 1 to remove the type error? And the third issue is that this error message is biased in that it attributes the type error to just to 1 only. And in fact, if we change true or either this x or this x, we are able to remove the type error. And the context doesn't tell us that 1 is the most likely error cause. Our second example is this type class definition collects, which is parameterized over 2 parameter types. So we can see here that CE denotes the type of the collect, and E denotes the type of the element. The function dependency here says that the type of the collect determines the type of the element. So for example, if a list of int is the collector type, then the type of the element must be int. So we can see that this function insert2 has a type error because it inserts 2 values, 1 and true, that have different types into the same collect. So if we load this program into Sherlock, it produces this error message. Sherlock usually generates high-quality error messages, but for this case, this message has 2 issues. The first issue is that it only attributes the type error to this insert or this insert. But indeed, if we change 1 or true, we're able to remove the type error. And actually, the paper that introduced this example indicates that the type error is due to the 1. The second issue is that the error message is expressed by using constraints, which is usually the internal representation used in implementing type inference algorithms. And showing them to language beginners may be too much for them. In this work, we try to improve this situation. For this expression, our approach generates this error message. It is just to change true to something else to remove the type error. We can see that our approach generates comprehensive error messages and is not biased. So we can see here that on the last line, if the user wishes, then we can keep on generate error messages until there are no more fixes. And also, as we may generate a lot of error fixes messages, we have to rank them so that we present the most likely ones to the user first. And we can also see that our message contains a lot of details to fix the type error. For example, if we say true had to be changed, then we say true had to be changed to this type to remove the type error. And if that is the case, then insert2 will have this type. And for example, if the user knows what is the target type of insert2, then the user can quickly use that information to decide whether this error message is useful and should be followed. Next, I will talk about how our approach find error fixes. Since our goal is to find comprehensive error fixes, we have to go through each sub-expression and decide whether it causes type error, and if so, how should we change it to remove the type error. So we can essentially reduce these two questions to a new type inference problem. Let's use this example to illustrate our idea. Let's see if we say we want to find out if one causes type error. So what we can do here is that we replace one with the variable called UV. Now we have a new sub-expression. And we try to run the type inference of this expression iteratively under the assumption that the UV has a fresh type variable alpha. And here alpha indicates that we can change one to something that have any type, since alpha is unconstrained. And there are two possible outcomes of this type inference. The first outcome is that type inference fails, which means that even we change one to something else that has any type, the expression still has a type error, which means that one is not an error cause. And it's also possible that multiple sub-expressions have to be changed at the same time together with changing one to remove the type error. The second outcome is that type inference is successful. In that case, we know that one is a real error cause, and it has to be changed to the type set applied to alpha to remove the type error. Here, theta is a substitution returned from this type inference process. So we can see that essentially we can go through each leaf to find out if that leaf is an error cause, and also find out what is the type it should have to remove the type error. So for example, if to find out whether insert causes type error, we run a, we solve a type inference problem. And we find out one, we have another type inference problem, and find out if both true and one cause the, both insert and one cause the type error, then we run another type inference problem. So we can see here that the problem is that we have to run a lot of type inference processes. And for example, in order to find out these three possibilities, then we have to run this sub-expression 3 times. And now this can quickly run into an exponential problem, as we have to consider all leaves and all combinations of the leaves, since in some cases, several leaves have to be changed at the same time to remove the type error. So our solution here is to reuse the typing process to make our approach scalable. Our insight is that even though this type inference have to run 3 times, but this sub-expression, the typing process is always the same. So if we have an approach to reuse the typing process, then we can reduce the complexity. And our solution is to create choice types for all leaves to reuse the typing process. I will next give some background on choice types. So choice types are introduced to type choice expressions, and we can consider we can view choice expressions as a discrete representation of C preprocessors. And each choice is named, as here we have a choice named A. And each choice has 2 alternatives, referred to as first alternative and second alternative. So we can eliminate the choice to get expressions encoded in this choice expression. By selecting the left alternative of A, we have even one, and to the right, we have successor one. Whenever we eliminate a choice, we must take exactly one alternative from each choice. Now let's see how we can assign types to choice expressions with choice types. Since this sub-expression contains a choice, it's natural that its type is also a choice over 2 function types for the respective functions. Now for the application to go through, we have to transform this type into a function type. And we can realize that through this type equivalence transformation, which essentially lifts error types out of the choice types. Now, if we look at this type, we can see that the parameter type is a choice between 2 same types. So what we can do here is that we can imagine that we can eliminate that choice. So now we can see that the parameter type and the type of the argument match it. And then now we can say that this expression is well typed and its return type is a boolean. Now we can see that how choice type can help us to find error fixes. So for this expression, even though it doesn't contain choices, but we can introduce choice types as we assign types to abs and true. For abs, because the type and the normal type inference is alpha2 to alpha2, so we recorded that type in the first alternative. For the second alternative, we assign the type as alpha3 to indicate that we can change abs to anything to remove the type error. Since alpha3 is unconstrained, so the idea is that we can change abs to something that has any type. Similarly, for true, we'll create a choice whose first alternative is bool, second alternative is again a fresh type variable. Now, in addition to assigning these choice types, we also need to collect constraints. So for abs, we have this constraint that says alpha2 must be a member of none in the left alternative. In the right alternative of A, we don't have any type class constraint for alpha3, so we use an epsilon here. Now, as we move to type abs applied to true, we have a type equality constraint. In this case, we can see that this constraint involves choice types. Now let's see how these 2 choice types allow us to encode all possible fixes to this expression abs true. If we change abs, but we don't change true, which is that we go to this style, and we can see that abs have type alpha3, which means that we can change abs to anything, but the type of true part will be bool. On the other hand, if we look at this style, which means that we change only true but not abs, then abs has type alpha2 to alpha2 as we can read from here. And the type of true is alpha4. So we can see that indeed these 2 choice types encode all possible fixes. Now we have alpha3 and alpha4, and we have to solve them. And we achieve that goal through this constraint solving. We begin by solving type equality constraints. Since this constraint involves choice types, we use the variational unification algorithm that we developed earlier to solve this constraint. And the constraint solving result consists of two components. The first component is a substitution, and the second component indicates where type inference is successful, where it fails. And in this particular example, since constraint solving is successful everywhere, we can say that we use a top sign to indicate that. Now we have a solution for alpha 2. We can plug in that solution into this type class constraint. And after that, we use an algorithm called variational context reduction developed in this paper to reduce this type class constraint. Again, the reduction result consists of two parts. The first part is a reduced type class constraint, and the second part is a pattern to indicate where reduction is successful and where reduction fails. So for example, we can say that in the first alternative of A and B, because we don't have an instance declaration for bool to be a member of num, so we have a bottom to indicate that context reduction fails here. But for this part, because num alpha 4 is already in higher normal form, we can say that context reduction is successful, indicated by this top sign. Now we have solutions for alpha 3 and alpha 4 and other type variables. And we can imagine that we have this typing process, and this is the final typing result. And this pattern here indicates where constraint solving is successful and where it fails. Now from these results, we can actually generate all possible fixes. For example, if we don't change x or x2, then it corresponds that we take this part in the first alternative of A and B. So we have a bottom sign to indicate that this expression is indeed ear typed. But if we choose the second alternative, if we choose to change true, but not abs, which means that we will take the second alternative of B and the first alternative of A. And we can see that we have a top sign here, which means that by changing true, we can indeed fix the type error. And moreover, we know what type true should be changed to, as in the blue color. And from this, we can actually have generate this type error message, and the color indicates where this information comes from. So this is how we generate type error messages. Okay, now I will present some evaluation results. For evaluation purpose, we created two benchmarks. The first benchmark consists of 17 programs from the literature that involve type classes and functional dependencies. The second set consists of 60 programs from the students' programs. Here I list some information in comparing our approach TEC against the Sherlock and the GHC. Each black dot indicates that the error message from the tool removes the type error. So we can see that our approach is quite effective compared to these two tools. And here are some statistics. Each number indicates that with certain number of error messages, what is the percentage of type errors that can be removed. For example, here we can see that with 2 error messages, our approach can remove up to 72% of type errors. Again, we can see that our approach is quite viable compared with these two tools. We also evaluated the response time of our approach. For programs with about 30 lines of code, it takes about 0.3 seconds. And for programs with 300 lines, it takes about 5.7 seconds. even though it takes quite much time, but we think that this time pays off for the users, as it usually takes much longer time to fix the type error. In some cases, our approach doesn't generate comprehensive error fixes. I would defer the discussion to the paper. We also have a formalization of the type system and an algorithm for variational context reduction, and also heuristics for ordering suggestions, and also more discussion about the evaluation. In the future, we plan to extend our idea to more expressive type system features, and we want to improve response times. Thank you for listening. I will now take all the questions that you may have.